Democritus proposed that all atoms are indivisible and indestructible.
As Democritus told us, an atom is an indivisible and indestructible piece of matter. As a matter of fact, the name atom means indivisible, because it's so small that it can't be broken down into any further units. An atom is the smallest unit that matter can be in while still retaining the properties of its element. So basically, if we were to take this piece of Play-Doh and keep cutting it in half until you couldn't cut it anymore, that would be the size of an atom. And eventually, we would get down to the size of an atom. There would be no knife sharp enough to cut it any further. And that is an atom. Oh, cheerio there, chap. My name's Charles Dalton, and in the year 1800, I was doing some thinking about these atoms that Democritus told us about. So, me in my laboratory, I was thinking, and through some of my studies, I was able to develop 6 rules or laws that govern all atoms, which make up all matter. Rule number 1. All elements are made of tiny, indivisible atoms.
Yeah.
Rule number 2. All atoms of the same element are identical. 999? 1,000. Oh, hello there. Another rule, shall we? Rule number 3. All atoms of one element are different from atoms of another element. Oh, careful there. I just see a sock in the bag. Would you like another rule? Rule number 4. Atoms can mix together physically or combine chemically in whole number ratios to form compounds. Oh, cheerio again. Rule number 5. Chemical reactions occur when atoms are joined, separated, or rearranged. I'm just going to smack this ball now. 4 down there! My neck! Oh, just bumping the old lambskin around. Rule number 6. Atoms of one element are never changed into atoms of another element during a chemical reaction. Score 1 for England!
Nobel Prize awarded to J.J. Thomson. And the crowd goes wild. Ah! Ah! Oh, hello there. I'm J.J. Thomson. I looked into the work of my friend Dalton about atoms, and I was inspired to look into them myself. I discovered that there were negatively charged particles inside atoms called electrons. To demonstrate these ideas, I made my plum pudding model. However, Brandon Gutierrez ate all my plum pudding, so I've recreated it using cookie dough and chocolate chips. The chocolate chips represent the negatively charged particles, or electrons, randomly dispersed throughout the atom.
Professor Thompson, Professor Thompson.
What do you want? Rutherford the teacher's pet.
Shh. Well, remember that gold foil experiment that I talked to you after class yesterday about? Well, I did it, and I think I discovered something really cool.
What?
Using my experiment, I discovered that there's a central positively charged nucleus in the middle of the atom with electrons hovering around and shooting around outside. Most of the atom is actually just empty space. Who would have known?
Rutherford used his gold foil shooting gallery in order to find out as much as he could about the atom. He was trying to find out the shape of the atom by bombarding the foil with positively charged particles. Then he would look at how the particles bounced off the atoms in the foil.
We will demonstrate this experiment with these black circles, which each have a different shape as shown on this piece of paper. We will use tiny marbles to swirl around the container in order to try to figure out what shape it is.
Alright, I think mine is number 11. The two lines that go parallel to each other with the line connecting them.
I think mine is the triangle.
Let's see. Oh, I was right. See?
Me too.
By using this ball and hearing how it deflects off the lines, I was able to discover and figure out what shape the line would be. That's kind of like how
Rutherford couldn't see
Rutherford couldn't see the atoms.
shapes, but he bombarded them with particles in order to figure it out.
Yes. As Rutherford showed us in his gold foil experiment, an atom is made up of mostly empty space. In order to demonstrate the proportions of an atom, we're going to show it to you on a larger scale.
This here represents the nucleus of our atom. And in order to show you the empty space, Owen and Chris are going to run to where the electrons would be if our nucleus was this size. See ya. "100 yards away."
Professor Rutherford,
Yes, Niels?
Bore's boring.
you still haven't graduated?
Just getting my money's worth.
Remember how you said that electrons were found randomly outside the nucleus? Well, I discovered that electrons were found in specific paths and called orbitals around the nucleus.
The more energy electrons have, the farther away from the nucleus they can be. Lower energy electrons are found closer to the nucleus, while higher energy electrons are found in the valence shell farthest away from the nucleus.
We will demonstrate this idea by dropping these marbles on the targets that we see here on the ground. I will be dropping this marble from my eye level to show an electron with higher energy, while Christopher will drop his marble from waist level to show an electron with low energy. As you will see, my marble will be farther away from the center as opposed to where Chris's will be closer.
Science rules. Inertia is a property of matter.
Let's take a look at our results. So under those white pieces of paper you saw before were pink carbon sheets of paper, meaning that all the marks that were made from the drops came through and landed on these pieces of paper. Our two friends dropped them 50 times each on each of the pieces of paper, one from eye level and one from waist level. The eye level one was supposed to demonstrate electrons with high energy. And as you could see, the results were much less consistent and they were more spread out further away from the nucleus represented by the center of the bullseye. This is representative of high energy electrons which are located further away from the nucleus in and closer to the valence electron shell. We come over here to our waist level drop and we see that the results are much more concentrated around the nucleus and much more consistent. This represents how low energy electrons are close to and around the nucleus of the atom. After learning about the scientific breakthroughs that led to our modern understanding of the atom, let's quickly review what we know today about the atom. So in the center, there's a positively charged nucleus that consists of protons and neutrons. The number of protons indicates what element the atom will be. Outside of that nucleus, there's some empty space, and on the other side of the empty space, there's an electron cloud. Now, these clouds vary in size depending on the type of element that the atom is, and the number of electrons is usually equal to or close to the number of protons in the nucleus. Together, this whole thing creates the atom, and atoms will come together with other atoms of different elements to form compounds, and then these compounds and raw elements make up the things in our world today.
Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. Let's say that balls are an element. This is a pool ball and this is a ping pong ball. They're both balls, so they're the same element, but this one has more neutrons, so it has a larger mass. These are examples of isotopes.
Sometimes elements form what are called ions. Ions occur when elements either gain or lose an electron and become either positive or negative. These positive and negatives allow various elements to combine. Much like this magnet is positively charged and this magnet is negatively charged, they combine.
All the way down here, very far away, lots of empty space.
A whole 100 meter, 100 yards.
Science.
That's an atom for you. That's one big ass atom.
Can we have an 18-minute blooper reel and just do 2 minutes of
This
science?
is a project. I think you can learn something just from watching it.
I think we should do our video.
Why you should never let us do a chemistry project by ourselves.
Would you know what you're saying?
I just make it up as I go.
Alright, perfect. Chris, why would you start filming?
Cutting was harder than it looks.
My Royce jersey came. It's awesome.
Positively charged particles in order to try to find the shape of the atom. Once
Snacks are
whenever he
God's
says
way of telling us that fruit doesn't have to be natural.
Oh, we got the mini cereals. These are my jam.
Dude, I love how you showed up late just to get food from his house. Like, that's...
I'm starving. I didn't eat anything before this.
Me neither, actually.
Oh, and they got board games too.
It's a weird combination. Oh, there's munchies, too. You missed those. It's like sitting in a circle, like, eating Welch's.
There's what wants his mood ring.
And you're going to put that into one of
Frodo.
these.
Marriage is over.
So you're going to attach
Frodo, you can have it back.
one.
I don't get that. Am I Frodo?
Tiger Woods here.
My neck!
Where are the Pop-Tarts?
I have no idea.
God damn. Jack, less chips, more Pop-Tarts. Oh, Hershey's Kisses. Can we open the Hershey's Kisses?
There's hydrogen and helium, then lithium, beryllium, boron, carbon,
We
everywhere.
got it.
Nitrogen all through the air, the oxygen, so you can breathe, and fluorine for your pretty teeth. Neon to light up the sign, sodium for salty times. Magnesium, aluminium, silicon, phosphorus, then sulfur, chlorine, and argon. Potassium, and calcium, so you'll grow strong. Scandium, titanium, vanadium, and chromium, and manganese. This is the periodic table. No gas is stable. Halogens and alkali react aggressively. Each period will see new outer shells will electrons are